Welcome to this interactive session on the top gas composition analysis. In this module, we will learn how to understand and interpret changes in blast furnace top gas so that a control room operator can take the right action at right time. The concept discussed here apply to any blast furnace worldwide, so you can directly relate them to your own furnace condition. Top gas analysis interactive training is going to be a very important part of this presentation. As we know, top gas analysis or composition variants indicate the changes in the process or efficiency in the fastest mode. Hence, it is required that top gas compositional analysis variance and it address towards the change in process and efficiency is to be well understood by each operator of the blast furnace to have a effective action. So what is top gas? Top gas, our off gas, is the gas that exits the blast furnace from the top. After cooling down from the raceway temperature of around 2200 degrees Celsius to roughly 100 to 150 degrees centigrade, that is our optic temperature, it mainly consists of nitrogen, which is inert and simply carries heat, along the active reducing gases, carbon monoxide and hydrogen. You will also see the reaction product carbon dioxide and water vapor plus small quantities of oxygen and methane. The key point is that top gas composition act like a live indicator of the reaction happening inside the furnace, giving the operator a continuous picture of uh, process health. So, coming to our journey of the uh, gases, uh, as we have just earlier discussed about the compositional variance. Now coming to our slide number 3, which follow a 5-step journey of gas through the furnace. In the raceway at about 2200 Celsius, coke is there, and there is a PCI coal is also injected along with the oxygen react to form carbon monoxide and hydrogen and nitrogen, and all of these are initially active gases. As the gas move up through the direct reduction zone around 1200 degree, more carbon monoxide is generated by solid carbon reacting with FeO. Around 900 degree, we reach the gas reduction peak where hydrogen becomes very effective and efficient, and roughly 35% of it is utilized for ore reduction. Between 600 and 900 degree, magnetite reduction continues and the gas composition start stabilizing. Finally, near 150 degree at the top, the gas leaves the furnace with its final composition, which we analyze in the control room. Now let's look at the key components of the top gases and their typical ranges. Carbon monoxide usually around 23 to 30% and is the primary reductant removing oxygen from the ore. Carbon dioxide is typically about 15 to 22% and represent the product of reduction. A higher carbon dioxide level generally indicates better gas utilization. Hydrogen is usually 2 to 5% and reduces ore very effectively at higher temperature, mainly coming from moisture and injectant. Nitrogen is the largest component at about 50 to 60% inert but very important because it carries sensible heat and reflects the blast volume. Water vapor is typically 2 to 4% and represent the product of hydrogen reduction. It also affects gas volume. Each of these numbers tells part of furnace story. Top gas analysis in so now we will see the one of the most powerful indicator for a control room operator is CO2 CO ratio or CO2 utilization is calculated as CO2 divided by sum of CO plus CO2 expressed as a percentage. For the most furnace, a normal range is about 45 to 50%, which correspond to roughly 30 to 35% CO2 in the gas being used for reduction. High CO2 values above about 25% generally mean good gas utilization or being reduced efficiently and a favorable coke rate. Low CO2 value below about 15% point to poor gas utilization, a possible cooling trend in the furnace and ultimately higher coke consumption. Remember that CO2 can only be formed when oxygen is removed from ore. So it is like a fingerprint of successful reduction. Coming to our next slide, which is a talk about temperature control chemistry. Temperature inside the furnace control which reactions dominate and therefore what gas compositions we see. Above about 1100 degrees Celsius in the direct reduction zone, FeO react with solid carbon to form metallic iron and CO, consuming a lot of heat and coke. Between 900 1100 degree in the gas reduction zone, Fe3O4 react with carbon monoxide to form FeO and CO2, and hydrogen is also very effective here with around 35% utilization. From 600 to 900 degrees, hematite convert to magnetite and then to lower oxide, and carbon dioxide becomes more stable in the gas. Below 600 degree the final stage of hematite reduction occur, but there is also a risk of carbon monoxide decomposition by Boudouard reaction which deposits fine carbon. The simple message is lower temperature generally produces more carbon dioxide, but if you cool too much, you risk carbon deposition, and carbon deposition is also like a hidden bomb. Many times it gets in the perforation of a material or refractory, and at a favorable range when there is a expansion it just burst. Now consider what it means when carbon monoxide in top gas increases. Possible reasons include a rising furnace temperature, increasing direct reduction, faster burden descent, a higher PCI rate or lower oxygen enrichment. For the operator this usually signals a warning trend, higher coke consumption and incomplete gas utilization. If this high carbon monoxide, high temperature condition persist, there is also a risk of overheating and carbon deposition. In such cases, the furnace often need to be cooled down through a suitable control action. Now, on the other hand, an increase in carbon dioxide in the top gas usually point to a cooling furnace. Typical cause includes slower burden descent, lower PCI rate, higher oxygen enrichment, or improved gas distribution. This pattern indicate a cooling trend with more effective gas reduction and a better fuel efficiency, while direct reduction tend to decrease. In such a situation, the operator may actually need to warm up the furnace slightly, for example by increasing hot blast temperature or other thermal input. Top gas, uh, mm, so coming to the hydrogen in top gas is often called the hidden reductant. It mainly comes from moisture in the hot blast, volatiles from the coal, and any natural gas that is injected. Typically about 40% of the hydrogen is utilized to remove oxygen from the ore, forming water vapor. When hydrogen levels are high, in the range of 4 to 5%, it usually indicates significant moisture or gas injection and allows some reduction work to be transferred from CO to H2, enabling lower flame temperature. Hydrogen reduces ore more efficiently than carbon monoxide at temperature above about 821 degrees centigrade and releases additional chemical energy. So natural gas injection can improve process stability and allow lower flame temperature without losing productivity. Now detecting the direct reduction is very important from saving of costly coke and heat. So detecting it early from top gas data is critical. The carbon used for direct reduction can be estimated as a difference between carbon input at 2 year and the carbon that lives in hot metal and top gas per hour. A normal range is about 90 to 110 kilogram of carbon per ton of hot metal consumed in direct reduction. If direct reduction increases together with an increasing Boudin descent rate, that is a clear sign of a cooling trend that require action. In such cases, operator should increase PCI or other fuel appropriately to avoid furnace chilling, and remember that the response in hot metal silicon. Oxygen balance in the Boden can also be linked to what you see in the top gas. For example, hematite ore, the starting oxygen to Fe ratio is about 1.46, corresponding to 3 oxygen atom per 2 iron atom. After gas reduction near 900 degrees, the Boden is at about magnetite level with oxygen to Fe close to 1, and by the time melting occur above 1200 degrees Celsius, the oxygen to Fe ratio drop to about 0.47 to 0.50 due to direct reduction. High CO2 in top gas generally indicate that this oxygen to Fe ratio is improving because more oxygen is being removed by gas. Excellent furnaces, often the natural gas and high efficiency, can reach 0 to oxygen to Fe ratio about zero point 0.4 to zero point 0.45, whereas values above 0.55 indicate poor reduction and high direct reduction consumption. Now suppose CO in the top gas rises from 26 to 32 within 1 hour, while CO2 drop to 14%. This combination suggests that direct reduction is increasing, Boden descent is accelerating, and the furnace is warming. The underlying reason is higher temperature in the cohesive zone causes more FeO to react with carbon to form Fe and CO. The operator's response should be to increase PCI rate promptly, then monitor hot metal silicon closely, ensuring it doesn't increase by more than about zero point 0.1. Boden descent rate should be watched for the confirmation, and if silicon continues to rise, a further PCI increase may be required. Now, in the second scenario, CO2 rises to about 24%, CO drop to 23%, and hot metal silicon falls from 0.65 to 0.45. These patterns signal a cooling furnace, slower burden descent, and improved gas reduction efficiency. The lower direct reduction near 900 degree zone allow CO2 to become more stable and being utilized. Here the operator should increase hot blast temperature to warm the furnace, expecting an effect within about 2 hours. If production need to be reduced, PCI may be cut back. But permeability indicator such as K factor should be monitored where blast temperature is already high. Auxiliary fuels like oil or gas can help adjust the thermal balance. Now, in the third scenario, we will see that hydrogen around 4.5%, blast moisture about 8 gram, and CO2 near 22%, and coke rate lower than the baseline. These combination usually mean that natural gas or coal injection is working optimally and overall reduction is very efficient. Hydrogen is replacing part of the reduction work done by carbon monoxide. Direct reduction is minimized and the thermal reserve zone is strong. In such a case, operators should maintain the existing PCI or gas injection rate because the process is already at an optimal point. Hot metal temperature may stabilize at a slightly lower level, but the high hydrogen levels at these injection rate can be safely maintained with a good productivity and without raising the flame temperature. Now, a warning about the Boudouard reaction in 500 to 550 degree zone when top gas containing high carbon monoxide cools through this temperature range. The reaction 2CO forming carbon plus CO2 can deposit fine carbon. These carbon can clog refractory, reduce heat conductivity and create brittle layers that fall prematurely. Practical indicator of this condition include high carbon monoxide above about 35% combined with a high top gas temperature about 150 degrees, black foam or unburned carbon at the water treatment plant and elevated methane in the top gas due to unburned coal volatiles. The preventive rule is simple. Do not allow sustained operation with both high carbon monoxide and high top gas temperature. So our top gas efficiency expressed as carbon monoxide efficiency is another powerful daily metric. It is calculated as CO2 divided by CO plus CO2 multiplied by 100%. Excellent furnaces achieve about 50% efficiency, which correspond to very good reduction, low coke rate and stable operation. A range of 45 to 50% is considered good and typical for many blast furnaces. Value of 40 to 45% are fair but should be monitored closely for trends, while any sustained value below 40% is poor and require immediate investigation for cooling or gas distribution problem. This parameter should be tracked every day as a key process health indicator. Now, blast moisture also leaves a clear mark on top gas and furnace thermal balance. A normal moisture range in the hot blast is about 10 to 20 grams per cubic meter. Every increase of 10 gram per cubic meter reduces flame by roughly 42.5 degrees Celsius. Because additional moisture must be heated and discussed in the top gas, higher moisture appears as increased H2O and elevated hydrogen content. This can support ore reduction and lower direct reduction, but it also increase top gas volume and pressure drop. Moisture is a slow acting control knob taking about 8 hours for full effect. So it is useful for gentle long term temperature adjustment rather than rapid correction. Top gas as for the oxygen enrichment of the blast is concerned, oxygen enrichment is another important lever affecting top gas composition. Normal air contains about 20.9% oxygen and typical enrichment level of 23 to 25%. Each 1% point increase oxygen raises the theoretical flame temperature by 33.9 degrees Celsius. In the furnace, higher oxygen result in more intense combustion at the tuer producing carbon monoxide and carbon dioxide while reducing the volume of inert nitrogen. This usually causes slight increase in CO2 utilization and a reduction in Bosch gas volume. Increasing productivity also. However, top gas temperature must be monitored because if it falls below about 110 degrees Celsius, overall furnace efficiency tend to drop, then it's a really indicating towards a big problem. Now, pulverized coal injection significantly influences both flame temperature and top gas composition. For a 10 kilogram per ton hot metal increase in PCI, the theoretical flame temperature logically drop by around 26 degrees. At the same time, additional coal adds both hydrogen and carbon monoxide to the Bosch gas and usually increases production. Because of the cooling effect, direct reduction may increase initially. PCI adjustment are relatively fast acting with a noticeable flame temperature response in 2 to 3 hours. For example, increasing PCI by 20 kg at constant flame temperature will tend to cool the furnace while keeping production stable. Initially, the CO to CO2 ratio will worsen, but over 3 to 4 hours, the system should stabilize at a new operating point. So gas distribution inside the furnace strongly affect what you see in the top gas analysis. When gas distribution is uneven, part of the gas can bypass the ore melting zone through channel, leading to poor contact between gas and burden. Typical signs of poor distribution include radial temperature imbalances at the top probes, sudden swing in CO or CO2 by plus or minus 2 to 3 percentage point occurs. Large silicon fluctuation and increasing permeability indices such as K factor. In such cases, the solution is to correct burden distribution rather than trying to manipulate top gas composition directly. Always remember that top gas is a mirror of internal furnace condition, so the root cause must be fixed inside the furnace. For the control room operators, disciplined daily monitoring of top gas essential. At least every hour record CO, CO2, CO2 over CO plus CO2, hydrogen content, top gas temperature and hot metal silicon. We have to plot 8 hours trend and focus on persistent rises or falls rather than isolated spikes. Red flag include carbon monoxide rising more than about 3 percentage point from the baseline. CO2 dropping more than about 3 percentage point continuously, or hydrogen falling below 1% when natural gas injection is running. When such changes appear, correlate them with a burden descent rate, pressure and permeability, and use a typical 2-hour response delay to forecast the future behavior of hot metal silicon. Several universal lessons apply to the top gas interpretation in any blast furnaces. First, top gas truly act as a process mirror. Every significant change reflects internal chemistry and temperature shift. Second, CO to CO2 ratio is a key indicator that link fuel efficiency to the furnace thermal state. Third, hydrogen is an ally because it allows lower flame temperature and more stable operation. Fourth, direct reduction, while necessary to some extent, is the enemy when it becomes excessive because it consumes coke and drive cooling trend. Fifth, top gas changes typically appears 2 to 3 hours before the hot metal silicon react, so they give valuable early warning. Finally, always make one adjustment at a time, wait a couple of hours, observe the top gas response, and only then decide on the next action. So the top gas composition analysis is the early warning system for the blast furnace operation. If you master The interpretation of CO, CO2, hydrogen and temperature trend, you can anticipate problems and control the furnace proactively instead of reacting after hot metal quality has already changed. Always adapt the numerical threshold and coefficient to your own furnace data. But the principles discussed here are the universal and can be applied to any blast furnaces worldwide.